Bismillahirrahmanirrahim. So my name is Adnan, and today I'll be presenting our work on TactileNet, bridging the accessibility gap with AI-generated tactile graphics for individuals with visual impairment. So according to International Agency for the Prevention of Blindness, about 1.1 billion people have some sort of sightless issues as per 2020 statistics, among which 43 million were blind towards the severe condition, nearly blind or who has very high power that needs assistance. So tactile graphics in this area, how it works is these are raised lines which basically presents the depiction of real world objects. So a visually impaired subject can move their hands on top of the braille embossed raised line textures to basically access this visual information in terms whether that be a braille embossed paper or whether that be a digital braille representation of the object. The problem with this is it's quite a developed discipline, the tactile graphic designing, but the graphics creation is labor intensive. It takes 10 to 15 minutes from simple objects like circle or a square to almost multiple hours for complex objects like butterfly. So with this in mind, we envision a scalable guideline compliant solution to basically generate these tactile templates. To envision it from the perspective of artificial intelligence or machine learning, we don't have large data sets. So one might say that these are just similar, they look similar to like edge detectors, edge detection does. But here I would like to draw your attention towards the forelimbs and the backlimbs, where we have the different texture, the differentiation, so that for a visually impaired person, when they roll their hand over the digital display or braille embossed paper, they can actually feel this distinction. And existing models like simple edge detection or segmentation methods won't be optimal in this case. And there is quite a lot of guidelines. For example, BANA guideline, which stands for Braille Authority of North America, which requires some strict rules and principles for it. For example, line and spacing constraints. So the contributions of our paper to basically envision it with the AI lens, not having that data set in first place, we try to close that gap for a machine learning pipeline. So we introduced TactileNet dataset, which includes 1,029 expert curated tactile graphics, which are scrapped from multiple tactile graphics libraries. For example, American Printing House for tactile graphics. And then these images are then scaled using our method to more than 7,000 generated images or templates, which are across 66 different classes. How we do it, our methodology includes parameter efficient adaptation of stable diffusion, which are popular generative models initially given by stability.ai, and we use methods like LoRa from Microsoft and Dreamboot by Google to basically adapt these models using our data set. Our evaluation includes human-centered evaluations from human expert designers, which actually work with education platforms for such schools, for subjects who have visually impairment. Results include 92.86% guideline adherence across sample set that we gave to these expert tactile designers. So a brief overview of our data set. It includes, as I said, 1029, more than 1,000 tactile graphics, which were initially collected from different libraries like APH Tactile Graphics Library, PRCBI, BTactile, etc. And then it is expanded towards more than 7,000 high quality images across 66 classes. So this is the table outlining the table from the paper, the different classes, which includes like common national images suitable for grade 2 or grade 3 level students, and which are quite useful in daily usage as well, like for example soda cans and shirt and so on. So the methodology, looking at the methodology, we start from scrap tactile images which are paired along with a prompt template. These prompt templates, we make a simple prompt template, and then using this image we give it to ChatGPT and DALL-E to basically see this image and then fill up this template to basically make up a prompt accompanying this image, and then that class specific prompt is then passed to our pipeline where using LoRa and Dreambooth, using these methods we adapt the stable diffusion model, anything V3, to basically, which is a text to image models, and that's why we are using the text here. So to use this text and image pairs to adapt these models and come up with a class specific fine-tuned adapter. Why class specific fine-tuned adapter? Because the limitation of the data. So for example, if you search for a dog class on APH library, you will come up with only 3 images. So we cannot have like a full fine-tuning here, and that's being why resource, not having that bigger data set, we adapt it to a specific class, and that's how we have 66 class specific adapters. In the testing phase, what we do is we take this adapter, we place it on top of a frozen stable diffusion model accompanied with a prompt, and here we make deviations which we'll present in ablations for the sake of generalization. And we give it a natural image at test time, and here we get a generated tactile image, which in this case follows the guidelines as given initially in the training phase. So these are the fine-tuning details. Per class adapters we have 66 models, and pretty conventional. We use LoRa rank 32 alpha with 16 and Dreambooth prior to the racial loss with weightage 1. Optimizer Adam WB 8-bit, and we use learning rate for unit to 1 ED⁻⁴, text encoder, batch size information, and so on. For the hardware, we use NVIDIA T4 for generation phase, and Titan V, that is given as a part of Google Collab for training, that is up to 20 epochs with early stopping. So that's pretty easy to train. It takes less than 5 to 6 minutes. 5 to 6 minutes. It takes 5 to 6 minutes to basically train a single class adapter. So going towards ablation, so for generation and control strategies, we use pretty much conventional stable diffusion models, default sampling methods, and classifier guidance scale here was varied for tricky classes. For example, removing water from the bottom of the duct, for example. And image-to-image translation then used denoising strength of 0.9 to retain the structure, and control net was used for some of the tricky classes which has a lot of complex elements like helicopter. Prompt editing and negative prompts were also used to basically make changes and make it editable in the training phase. So for example, on the left we see that a shirt with a logo and a pocket that is generated, and then adding that logo as a negative prompt, it just removes it. And then the pocket was removed from the initial prompt template to basically get a different version of the given shirt. So as a baseline, for when we talk about image editing tasks, instruct pix-to-pix is one of the first go-to methods that that are used basically. It's state of the art. So as a baseline, we choose instruct pix-to-pix. But the problem was, because of the less data that that is currently available in first place, it was really easily overfitting to the prompt, the class prompt pairs. So even after augmentation, like we multiplied the given prompt set multiplied by 1000 to basically make augmented version of the given images and text prompts, still it had these undesirable effects where it was just confusing apple with tomato, for example. And this is why it motivates the parameter efficient adapters instead of using a full-fledged one generalizable model, which is of course the future work. So for the evaluation protocol, blind expert evaluation was done. For example, each natural reference image was paired with the help of our volunteers at our lab to basically come up with two versions of it. One was generated and one was the scrap image taken from the libraries. An expert was asked to basically rate these images based on the questions: how does it align related to its pose and features? So given a natural image, how does a source image and a generated image aligns better with the given natural image? And the expert was blind to knowing which one is source or which one is generated. There was also another question like BINA guideline adherence and open comment feedback for future research. The scoring for binary, the scoring was done as binary 0-1 for question 1 and question 2, and for question 3 where we included categorical categories like whether you would accept this image as is or with minor edits, with major edits, or it's reject all in all. So these are the key results. The generated graphics, although less than source images, which was 96.43, we did achieve 92.86 BANA guideline adherence, and the quality breakdown, for example, generated except as this image was 32.14%, minor edits were 39.29%, and major edits included 28.57%, and we didn't have any image that was rejected. So they were, based on the feedback from the expert, we came up with the conclusion that they are useful in one way or other way. So these are the qualitative insights taken from the paper, just comparing the generated image and the source image, and then the natural images given as a reference. Just for the sake of time, some of our future work includes dataset diversity and moving towards using this dataset to have a generalized class unified model, and then for future including more hybrid ways of perceptual or tactile metrics and coming up with those. So with that, I would conclude TactileNet is a first of its kind dataset, and we invite all the researchers interested in accessibility and AI for social good to see it and collaborate with us. Thank you so much, and in the world of digital transformation, accessibility shouldn't be taken as an afterthought. It is a fundamental right for all of us and for all those who need it. Thank you.
So I guess we have 1 minute for questions, if anybody has questions for the presenter. Any questions? All right, thank you so much for your presentation.
Thank you.
So now it's time for the third presentation.